for this afternoon session is Fei Yang from Nanjing University, and he's going to talk about rational maps with smooth degenerate Herman rings. Please.
Okay, thanks. First, I would like to thank the organizers for providing me this opportunity to give a talk on this conference. I'm sorry I couldn't come to a better level in person. I hope I have a chance next time. I will talk about smooth degenerate Herman rings of rational maps. As early as 100 years ago, Fadou had a plan to study the invariant analytic caps of rational maps. However, he did not carry out it as far as we know. One of the motivations to study the invariant caps is to give the composition of the dynamics of meromorphic functions, meromorphic maps. This problem was active in 1980s. Avila proved that if gamma is an invariant Jordan analytic cap and an n-type function f, then either gamma is a circle and f is conformally conjugate to z to the n with n an integer, or gamma is a level cap of the linearization function of some Siegel disks. For rational maps, it is well known that an invariant analytic caps can have the following types: cycles, level caps of linearization functions of Siegel disks or Herman rings. In 2012, Eremenko found two types of Jordan analytic caps, which are not circles and invariant under the lattice maps. And moreover, the restriction on each of these caps is not a homomorphism. If the invariant caps are allowed to be smooth of some degree, but not necessarily analytic, then the related results become rich. For example, there are a large number of C1 smooth invariant caps in the parabolic basins, which are the level caps of Fadou coordinates. It is also known that the boundary of rotational domains cannot be analytic caps by Schwarz reflection. However, they can be smooth. Marco, Avila, Buff and Chéritat, and Jair proved the existence of Siegel disks with C-infinity smooth boundaries. Buff and Chéritat also constructed the Siegel disks whose boundaries are Cn but not Cn plus 1, C0 but not third continuous, and so on. Avila, Buff and Chéritat constructed such examples by successive perturbation. Moreover, Buff and Avila proved the existence of Herman rings with C-infinity smooth boundaries. For Blaski products, they automatically have an invariant unit circle. By choosing suitable parameters, one can grant that the restriction of these maps and the unit circle is conjugated to an irrational rotation. For example, we consider e to 2 pi I t z squared times z plus z minus a over 1 minus az. When a equals to 4, there exists t such that the unit circle is contained in a Herman ring. If a equals to 3, then there exists t such that the unit circle is contained in the junior set. In some things, the right hand is the degenerate case of the left one. To find more invariant Jordan caps which are not circles with such dynamics, we use the following definition. By a degenerate Herman ring gamma of a meromorphic function f, we mean a Jordan cap which is not a spherical circle satisfying the following properties. The first one is gamma is contained in the junior set of f. The second is gamma is not a boundary component of any single disk or Herman ring of F. The third one is gamma is invariant, and the restriction of F on gamma is conjugated to an irrational rotation. For the cubic Blaski product e to 2 pi I t z squared times z minus 3 over 1 minus 3z by a standard quasi-conformal surgery, which changes the super attracting fixed point at 0 to a geometric attracting fixed point. Then the resulting cubic rational map loses the symmetry, cannot keep any circle invariant, and has a degenerate Herman ring, which is a quasi-circle. Moreover, the smoothness of this quasi-circle is not known. 2 years ago, in the open problem session of the conference with the same title, Eremenko raised the following question: do there exist smooth degenerate Herman rings? Here in the following, when we say smooth, it means C infinity and smooth. The main purpose of this talk is to give an affirmative answer to Eremenko's question. We proved that there exist cubic rational maps having a smooth degenerate Herman ring. The main idea in the proof includes the following 4 parts. The first one is the construction of smooth Siegel disks by Avila, Buff, and Chéritat. The second one is the classical Siegel-to-Herman quasi-conformal surgery by Shishikura. The third one is control of the north of Lebesgue measure of a quadratic field in junior cells by Buff and Chéritat. And the last one is the study the rigidity of the cubic maps having bounded type Herman rings. We would like to mention that Avila's construction of smooth Herman rings does not need the latest 3 parts, since his perturbation can be done in the 1 parameter family with the parameter t, with the given a, which is greater than 3. Now let's give a sketch of the proof. We first need some definitions. Let alpha be an irrational number. Pn over Qn be its nth convergence. If alpha is of Bruno, then the quadratic polynomial P alpha has a Siegel disk that alpha centered at the origin. There exists a unique normalized conformal map phi alpha defined from a rounded disk d r alpha to the Siegel disk delta alpha, which conjugates the rigidity the rotation r alpha to P alpha. The number r alpha is called the conformal modulus of delta alpha. We use the Siegel-to-Herman quasi-conformal surgery. For any given Bruno number alpha, we paste 2 quadratic polynomial P alpha and P minus alpha along their Siegel disks together and orbiting a quasi-regular map F alpha. The quasi-regular map F alpha can be constructed such that there exists a quasi-conformal map phi alpha, so that F alpha is conjugated by phi alpha to a cubic rational map Q alpha. This map has 4 critical points: 0, 1, infinity, and C. And it has a Herman ring A alpha with the rotation number alpha and the conformal modulus 1 over pi times log R alpha over R. By studying the complementary information of Q alpha, we prove that the area of junior
sorry,
set.
can I? It's going. I just need to digest that for a moment. But so F alpha, your capital F alpha, that's your quasi-regular model map. Is that?
Yes. Here. Yes, to quasi-regular map a big F alpha.
Okay, so F alpha is your quasi-regular map, and then you straighten this to an actual rational map.
Yes, yes,
having the
yes.
having the Herman ring. And the key thing is, sorry, if you go back to your theorem or lemma.
Yes.
So what is the key thing here? The key thing here is that the modulus of this Herman ring is controlled in terms of the radius. Let's see.
The radius, yes, conformal radius and the R. Actually, here we skip some details because you paste the outside of this curve into put the outside here, and then you interpolate this annulus.
Okay,
You can
so you have a choice of which little r you choose in your construction, and this will change your modulus.
Yes, yes.
Your resulting.
Yes.
Okay. So this is, and then you want to make this modulus. You want to degenerate these rings by making this r going to 0, I guess. Is that no? Sorry, going to r.
No, not
going the other way. Going to r alpha, right?
Yeah. I change r alpha, not change r. I perturbate r alpha, and I have a sequence of alpha n, and then change alpha r n. Not we don't change r.
Okay. All right. Okay. Yeah. If you go back to the next slide, then sorry.
Okay.
Yeah. Please continue.
You're very welcome. So we have cubic rational maps Q alpha. It has a Herman ring with definite modulus, and then we also have the following lemma for any. We prove that the area of the junior set of Q alpha has the area of the junior set is 0 if only if P alpha, the junior set of P alpha has area 0, and moreover if alpha is of bounded type, or more generally if alpha is Peterson and Zachary type. Peterson-Zachary type is here. Then each component of the boundary of the Herman ring A alpha is a Jordan curve passing through exactly one critical point, and the area of the junior set of Q alpha is 0. Actually, in the whole proof, we only need to consider the perturbation of bounded type irrational numbers, but some major results are true for Peterson-Zachary type irrational numbers, because such irrational numbers incorporate the full measure in the irrational numbers. So we state some results for Peterson-Zachary types, but we only use the fact that we only use the bounded type case. And we also need the following rigidity result when we perform quasiconformal surgery. Suppose alpha is of Peterson-Zachary type, R lies between 0 and R alpha. R alpha is the conformal radius of the Siegel disk of P alpha, and theta is is a given number between 0 and 2 pi. Then there exists a unique A and a unique U depending only on alpha, R, and theta, such that the following cubic rational map QAU has a fixed Herman ring A, or say it is A alpha R theta in C, satisfying the following 3 properties. QAU has a Herman ring A of rotation number alpha, and the modulus of A is 1 over pi log times log R alpha over R, and the boundary of this Herman ring are Jordan curves passing through critical points 1 and C respectively. And the conformal angle between 1 and C is theta. The conformal angle means we measure the angle in a standard annulus by a conformal coordinate transformation. So this lemma tells us the pair AU, and hence the formula QAU is uniquely determined by these three parameters alpha, R, and theta. So in the following one, we use QAU and Q alpha R theta alternately under the assumption star. So these three parameters determine this formula uniquely. In Avila Buff's proof of the existence of smooth Siegel disks, the following lemma plays a crucial role. It describes the changes of conformal radius of quadratic Siegel disks under the perturbation of rotational numbers. It says that for any Juno alpha, any bounded type lambda beta, and any radius R naught between 0 and R alpha, let alpha n defined like this. We can see it has a big AN here. The AN tends to infinity very fast, but it depends on R alpha and R naught. The name is a QN here. Then we know this alpha n is also a bounded type numbers. Alpha n is a bounded type number. It tends to alpha as n tends to infinity. And the conformal radius of P alpha of the Siegel disk of P alpha n tends to alpha naught. Alpha naught is smaller than R alpha. And for any epsilon, for any positive epsilon, if n is large, then P alpha n has a repeating cycle, which is epsilon close to phi alpha T alpha naught. Phi alpha T alpha naught is a red cap like this. If n is large enough, then P alpha n has a repeating cycle, which lies in this narrow part. It is very close to this cap. To find degenerate Herman rings, we also need to study the Siegel-to-Herman surgeries continuity. Let alpha, R, and theta be defined as before. There exists a uniquely normalized conformal map chi alpha R theta defined from a rounded annulus to Herman ring A alpha R theta, which conjugates the rigid rotation R alpha to Q alpha R theta. By high type numbers high type n, we mean the set of irrational numbers whose continued fraction expansion with all coefficients greater or equal to a number big N. This type of irrational numbers was introduced by Eno and Shishikura. Let big N be a large number such that the near parabolic renormalization operator can be acted invariantly many times on P alpha when alpha belongs to HTN. The male lemma of our result is the Herman ring version of Avila, Buff, and Chéritat's lemma. For given alpha in Peterson-Zachary type and the high type R naught is in R and R alpha, and theta is given. We set alpha n equals to a number which is very similar to this number, but we use big N here to replace the T1, T2, T3. We use big N to replace the numbers. And the AN is the definition of AN is the same. Then we have alpha n tends to alpha, R alpha n tends to R naught. This means conformal radius, and the map Q alpha n R Q tends to Q alpha R n, because alpha n is a bounded type, and if we give bounded type and the R and the theta, then it uniquely determines a rational map Q alpha n R theta. So this is the first conclusion. The second is we also conclude that the chi, the nearization maps chi alpha n R theta also tends to the limit chi alpha R theta locally uniformly in this standard annulus as large n tends to infinity. We use large n because when n is large, then this map has definition in this annulus. And the third conclusion is that for any epsilon, positive epsilon, if n is large, then this cubic rational map Q alpha n R theta has two repelling circles, which are epsilon close to these two caps. Chi A alpha theta T R not over R, and this symmetry, this not symmetry, this another smooth cap. And the key point in the proof is we need to show the convergence of phi alpha n. We construct the Q alpha n R theta by quasiconformal surgery. It is a conjugate of the quasi-regular map F alpha n. We can show the convergence of F alpha n. And we also need to show the convergence of the quasi-conformal mapping phi alpha n. But the convergence of phi alpha n is in order to show the convergence, we need to study the quadratic Bayesian differential. The convergence of quadratic of Bayesian differential. This is based on the control of the north of area of quadratic field in junior cells, and this depends on this is the only place where we need to restrict the irrational numbers to be of high type. For the proof of the smooth degenerate Herman rings, we consider the convergence of smooth caps in fractured space, which is a complete metrizable locally convex vector space. A particular example is the collection of all smooth functions defined from the circle to the complex plane. With all the above preparations, we can prove the following more detailed version. Assume that alpha is a high type number and also bounded type, and R lies between is less than R is positive number less than R alpha. Theta is given in is a number in the interval in the open interval of 0 to pi, and the epsilon is a positive number. Let GT be a smooth Jordan curve chi alpha R theta e to 2 pi it, and then we can also use another formula to denote Q alpha R theta. It is QAU. Then there exists another irrational number alpha prime in the high type of high type numbers, such that and the cubic rational number Q A prime U prime and the C infinity embedding H, such that the distance between A and the A prime, alpha and alpha prime, U and U prime are very small, and can be arbitrarily small. And the the image of the unit circle on the H is a smooth degenerate Herman ring of QA prime U prime with the rotation number alpha prime, which is accumulated by repelling circles from both sides. And the G and H are epsilon closed in the fractured spaces. The proof is based on using the male lemma inductivity. Is based on using this lemma inductivity by perturbating the cubic rational map Q alpha n R theta to Q alpha n plus 1 R theta and so on. As n tends to infinity, the modulus of the Herman ring tends to 0, and there exists a limit smooth cap which is invariant under the limit cubic rational map. The second part of this talk is about the Lebesgue measure of the junior cells of the maps constructed just now. As early as the beginning of last century, Badu already considered the area of junior cells of rational maps. There are very fruitful results about the junior sets of rational maps with the error zero. On the other hand, until the beginning of this century, Buff and Chéritat proved the existence of low well-dense junior sets of rational maps having a junior set with positive error. Their example have three types: Siegel, cream, and the infinity set-net renormalization with unbounded completorics. Later on, Avila Dudko constructed another two types of infinity renormalizable quadratic polynomial with a junior set of positive error. Hence, for rational maps, the no well-dense junior sets with positive error are only known to appear when the maps have an irrationally indifferent periodic points and invariantly many renormalizable. By quasiconformal strategy, one can construct a rational map having a Herman ring and also a junior set with positive error. By the idea of constructing smooth degenerate Herman ring, we prove that there exist cubic rational maps having a no well-dense junior set of positive error, for which these maps have no irrational indifferent periodic points, no Herman rings, and are not renormalizable. Intuitively, such rational maps can be seen to be obtained by pasting two quadratic Siegel polynomial and known as Siegel disk boundaries. Recently, we only give another method to construct non-trivial degenerate Herman rings, not by quasiconformal deformation of Blaski products, based on the study of a priori bonds of bounded type Herman rings. The degenerate Herman rings constructed there are quasi-circles passing through critical points. For our examples, the degenerate Herman rings does not pass any critical points. In 2012, Eremenko asked the following question: does there exist a Jordan analytic invariant cap of a rational map different from a circle which is mapped onto itself homomorphically and intersects the junior set? This question is more challenging for degenerate Herman rings. That means, do there exist analytic degenerate Herman rings? I don't know the answer. This is a very challenging question. And finally, we collect some questions appeared in the study of degenerate Herman rings. The first question is, does there exist a smooth degenerate Herman ring whose rotation number is not of regional type? In our proof, we use quasiconformal strategy. If the rotation number is not of regional type, then it is hard to use quasiconformal strategy by pasting single disks. The second question is, does there exist a degenerate Herman ring which is not a quasi-circle? Note that Eremenko's question about the degenerate Herman ring was asked for meromorphic functions, not only for rational maps. So the third question is, do there exist a smooth degenerate Herman ring for transcendental meromorphic functions? And the last is a fourth question: do there exist at the most a finally renormalizable polynomial without irrationally indifferent periodic points whose junior sets have positive error? It seems that the answer to this question is negative by the work of Nipich and Shishikura. Thank you very much for your attention.
Thank you very much for your nice talk. Are there any questions for our speaker?
Hi, Fei Yang. This is Willie, actually.
Nice to meet you. Hey.
I was wondering if you if you found of any like numerical approximations of the pictures, what it looked like, of the examples that you made here.
Oh no, it's very difficult to draw the corresponding pictures, I think.
Yeah.
I think you have drawn many nice pictures of degenerate Herman rings containing critical points, but
they're easier. That's why I was asking you as well. Yeah. The second question actually. Do you know what the topology of the post-critical set looks like as well?
Oh, that's a very good question. I think the topology of the post-critical set can be corrected very well by the work of Dawood Shahi. He has give a topological characterization of the post-Greek set of quadratic polynomials when the resolution number of high type. So I think in our case, we can also give a similar characterization of the post-Greek set of the cubic rational maps obtained by this kind of quasi-conformal surgery. I think.
Thank you.
Thank you. You're welcome.
Thank you very much. That was quite a tour de force. A quick comment about your question with meromorphic functions. One might hope that you could do something where you take an entire function, a family of entire functions, having some, let's say, quadratic-like restrictions, and again, just glue in a quadratic polynomial in order to get meromorphic functions if you really wanted to. Does that make sense?
Yes. I think this is a very good idea. Yes, to first find the entire functions has a polynomial-like, quadratic polynomial-like restriction, then do the same quasi-conformal surgery. Yes. I think this is a very, very clever idea. Yes, I didn't. Yes, I think it works. Yes, it's a very good idea. Yes.
So there's one thing that I found quite striking in your your maps. They have the two critical. Oh no, sorry, your maps don't have the two critical values on the degenerate Herman ring, but somehow you had this parameter theta, right? So if I remember correctly, so this parameter theta kind of tells you conformally where your critical points are on the boundaries of the Siegel disk, right?
Yes. Theta is the conformal angle of these two critical points.
And then, if I understood correctly, in your construction, the theta stays fixed. So you're fixing the theta, and then you sort of take a limit.
Yes.
So
the theta is fixed.
So presumably, if you take different thetas, you will get different. I mean, I don't know whether is that clear. Would you get different maps? And if so, what does the theta mean for your limiting map? Is there any? Do you have any idea?
Yeah. Because it's a very good question. When we take limit and the alpha n are all of bounding type, then we can see these two critical points on the boundary of Herman rings, and then we can measure their conformal angle always equal to the theta. As we take limit, then we only have a degenerate Jordan curve. Then these two critical points are not on the degenerate Herman ring. They only nice on the hairs, like hairs attaching to the degenerate Herman rings. I think there's some ways to measure their angles.
Yes, so
from
I
both
guess,
sides.
So we should think of your thing. You have like a hairy circle or something. Like you have one-sided hairy circle, and you've got another one, and you're gluing them together, and some of the theta determines how they are glued together. But it's kind of funny that it's an analytic thing, right?
Yes. This is a fair. I think this is yes. It's like a hairy circle. Yeah, to paste two hairy circle together like that.
They're very intriguing. Thank you.
Yes. Thank you for your question.
Any more questions? Well, if not, let's thank our speaker again. And
thank you.
Continue tomorrow.
Thank you, everyone. We will resume tomorrow.